How accurate is terrestrial laser scanning, and how do factors such as overlap between scans and density of applied survey control affect the final accuracy of a point cloud derived from a group of scans linked together? These questions are why I spent between 200 to 300 hours on this video acquiring data, processing data, and analyzing data to do my best to try to find some of these answers. Ask a manufacturer what the accuracy of their scanner is, and 99 times out of 100 you'll get the specification sheet answer, which is not the accuracy of the point cloud deliverable of that scanner being used in the field after aligning multiple scans together. It's often a ranging standard deviation of a single scan in a laboratory, which doesn't really help us much. Today we're going to look at 4 project sites, 15 data sets, and over 3,000 check shots on real-world projects getting real-world results. We're talking about terabytes of data here that has resulted in some very fascinating observations. I hope with today's video I can spark a long overdue discussion about both what kind of real accuracy can we really expect from a processed point cloud of a terrestrial scanner, and more importantly, what effect does the density of survey control applied to that point cloud have on the accuracy of that data set? All 4 project sites involved in this study were scanned with Leica's RTC 360 terrestrial scanner and processed using Leica's Register 360. The RTC is a tried and tested scanner that's been around for over 6 years and has proved itself time and time again at being an accurate and efficient staple in the industry. Register 360 is a relatively straightforward and easy to use piece of processing software that does a fine job of registering the scan data of the RTC. Each project was scanned in the field using slightly different techniques in order to answer the question about how field scanning practice affects accuracy. I will expand on this more when we start looking into each project site. That being said, all project sites used black and white scanning targets both as check shots and as applied control. The scan data was processed in Register 360 in a fairly uniform manner. For every single project site, each scan network dataset was built by connecting every individual scan using the links created in the field at the time of scan, but additional links were also created in the office to improve cloud-to-cloud registration. Moving objects were detected and removed, and besides some minor adjusting of problem links, there wasn't too much manual manipulation of the scan network linking. The first data set for every single project site was 100% reliant on cloud-to-cloud registration with no control being applied. Automatic target recognition was turned off on import, as I did not want the uncontrolled datasets to be influenced in any way from targets being within the project site. The processed uncontrolled point cloud was then exported in the scanner's local coordinate system for analysis. The 4 project sites were then processed again using control at varying densities. For example, project site 2 was processed with 0, 3, 6, 12, and then 20 control points applied, creating a bunch of separate datasets. For the datasets with control applied, I unlocked the links of the scan network and optimized the bundle with the checkbox prioritize targets in cloud-to-cloud being turned on, as to ensure that the control points were taking priority in the adjustment. What exactly do I mean when I say cloud-to-cloud registration? Register 360 uses a version of the very common ICP, or iterative closest point algorithm, to merge 2 or more individual scans together. This is more or less what they refer to as cloud-to-cloud registration. ICP is basically a 2-step process: data association and transformation based on that data association. It combines the individual scans in such a way that the points it has determined to be common between both linked scans are shifted and rotated so that the sum of the squared distances between the common points is reduced as much as possible by taking an iterative approach. It shifts the cloud being compared to the reference cloud, measures the square of the sum of distances between the common points, and if that value doesn't meet a set threshold, it tries again and again until it either fails to meet that set value or converges and successfully links the two or more scans together. If you've seen any of my least squares videos on survey processing, it's not too dissimilar to that at all. There are many variants of the ICP algorithm that take a slightly different approach, and unfortunately Leica does not disclose exactly how their ICP algorithm works. And further to that, I could not find any information on exactly what weighting is used when applying control. Quite the contrast to a program like StarNet, where you not only know exactly what weighting is being applied, but you also have full control to change that weighting. The result is that to try to infer on what is going on in Leica's black box, we must run tests and make observations, hence why this video came to be. Once all 15 datasets were processed, I exported them as RCS files and used Autodesk's recap and its note tool to extract coordinate values from the center of each black and white target within the dataset. Those coordinates were then brought into either StarNet or an Excel spreadsheet to begin the accuracy comparison. When a dataset was registered without control, I could not simply compare the coordinate values of the extracted target center from the point cloud with the target values obtained from the least squares adjusted total station control network for the same target, because the point cloud was in the scanner's assumed coordinate system and the total station values were georeferenced in a separate known coordinate system. So instead, these point cloud derived coordinates for the targets were used by inversing distances between points, and those distances were compared to the inverse distances between corresponding targets that were shot in with a total station. This will be referred to as the inverse distance method. For example, I picked what I deemed to be the center point of the black and white targets out of a point cloud for targets 5158 and 5162 on the parking garage dataset and got their coordinates in the scanner's local system. When I inverse between those 2 points, I got a horizontal ground distance value of 315.918 US survey feet and an elevation difference of negative 0.538 feet. When I inversed between the coordinates of those same 2 targets as they were defined via reflectorless measurements that were taken from the total station control network, I got a horizontal ground distance value of 315.882 feet and an elevation difference of negative 0.560 feet. The difference between those 2 horizontal and vertical distances were 36 thousandths of a foot and 22 thousandths of a foot respectively. This method was used for all project sites when no control had been applied. The inverse distance method was also very helpful to identify any issues with relative accuracy of a dataset between separated areas, such as between floors or between buildings. Average residuals were calculated to help condense the dataset comparison to a manageable level. After control had been applied, I could now directly compare the values between the total station control network coordinates for the black and white targets and the coordinates extracted from each point cloud for those same targets. A distinction was made using this method of comparison between all targets and the independent check shots, or the targets that had not been used as applied control, as it would stand to reason that if a target had been used as control, then there would be too much correlation between that target in the point cloud and the comparison coordinate value that was used to align it. This correlation was overwhelmingly obvious as I started to go through the data. The first project site was a 15,000 square foot industrial site that included a long conveyor belt of different machinery that was used to manufacture roofing materials. I placed 21 black and white targets total and performed 140 scans with a scan density of 107 square feet per scan. This was a very active site with a lot of pedestrian traffic and moving machinery that had to be cleaned out of the scan, which should have theoretically affected the cloud-to-cloud registration. There was, however, a lot of hard, flat surfaces in every direction to counterbalance this by giving the individual scans a lot of geometry to use during alignment. 11 baseline distances were created from the 21 black and white targets that were used in the inverse distance method of accuracy comparison. With no control applied, the average horizontal distance residual was 8 thousandths of a foot or 2 millimeters, and the average vertical distance residual was 6 thousandths of a foot, also 2 millimeters. So what I'm basically saying is that I inversed between the 21 targets 11 different times using the total station coordinates for the targets and the coordinates extracted from the point cloud, and the values I'm quoting are the average of the difference between those inversed distances. Again, no control was used. There is nothing tying the total station coordinates to the point cloud coordinates. I find it pretty shocking that this level of accuracy is possible, considering it includes random error from the total station control network, the cloud-to-cloud registration, and manually picking out the center of the targets in the point cloud. Some may make the argument, how are residuals that small possible when the control network shouldn't even be that accurate? Normally, that would be a valid argument. However, great precaution was taken when establishing this control network and the control for the other project sites as well. For reference, the standard deviations of these total station coordinates were floating around 1 or 2 millimeters. Error values this low take special tools and field and office techniques to achieve, a topic for a video on another day. 13 control points were then applied to the same project site. This time, both the average horizontal and vertical distance residuals were 7 thousandths of a foot or 2 millimeters using the inverse distance method. So we went from 8 and 6 thousandths of a foot to 7 thousandths of a foot, effectively no change, a fraction of a millimeter. Using the coordinate comparison method, the average residuals for the northing, eastings, and elevations were 5 thousandths, 4 thousandths, and 6 thousandths of a foot, or ranging between 1 and 2 millimeters. Again, this only includes residuals from the independent check shots. As we can see, both datasets were extremely tight and extremely accurate, but control neither had a positive nor negative effect on the accuracy. I suspect this was because the cloud-to-cloud registration had a lot of overlap to work with. There was a high density of scans, and the fact that all the scans were on one floor without narrow hallways to work through, and there were also a lot of links relative to the number of scans. Besides all the people and machinery moving around, these were some ideal scan conditions. For the second project site, I wanted to choose a location that had multiple floors, and I also wanted to space out the scans a lot more to see how the reduced overlap would affect the processed point cloud. We went from a project area of 15,000 square feet on the first site to 260,000 square feet over 3 stories in a public parking garage with over 349 scans and 32 black and white targets being set. There was also a lot of repetitive geometry, moving cars and pedestrians walking around. On the second and third floor, every time a car drove by, the floor would shake significantly and the RTC would display a warning that movement had been detected. The scan density went from 1 scan every 107 square feet to 1 scan every 744 square feet. Before I saw the data, I had a feeling that this would be a much more difficult project to produce accurate results without a significant amount of control. The intent with the selection of this site was to test whether or not cloud-to-cloud registration could sufficiently align the scans together to obtain an acceptable level of accuracy when the project stretched between different floors connected by narrow stairwells, and the majority of the scans were spaced out 30 to 40 feet from each other. The first data set we'll look at used the inverse distance method of comparison only, as there was no control applied yet. Once again, I was pleasantly surprised by the check shots comparison. Average horizontal and vertical residuals of 14 thousandths of a foot or 4 millimeters and 24 thousandths of a foot or 7 millimeters respectively were observed. Now these values are relatively quite a bit higher than the first project site, but keep it in mind that this project is almost 20 times the size and spread across multiple floors. To be able to obtain an average error of 1/4 of an inch that I'm seeing here with zero control over a project this size is pretty phenomenal and much better than what I had expected, especially considering the less than optimal scan conditions. That being said, I'm fairly certain the scan density being reduced by 7x on this project had something to do with the increase in error. An interesting point I would like to highlight on this uncontrolled dataset is that the error between points on different floors were no worse when comparing points located on the same floor. For example, the average horizontal and vertical residuals between all the points on the first floor and all the points on the third floor was 16 thousandths of a foot or 5 millimeters both horizontally and vertically, which is actually better than the overall average for this entire data set. Something to keep in mind when looking at these numbers. It's easy to see a 6 millimeter average residual for one data set and 8 millimeter for another and think that the first data set must be 2 millimeters better than the second. You could make that argument if we had data sets with a massive amount of data points being used in the comparison and random error didn't exist. But in this situation, as in most, random error is real. So think about these numbers as a range. When I say the average residuals were 6 millimeters, mathematically that's true, but it's really more like 6 millimeters plus or minus a few millimeters here and there. We have to look at trends here and consider all the sources of random error that are affecting our measurements. Fortunately, many of those sources of random error are constant between data sets on the same project site, which allows for the change in error to give us a sense of what is going on as we change how the data is processed. The next data set for this project site we are going to look at has just 3 control points applied to it, just enough to georeference it into place. Using the inverse distance method, average horizontal and vertical residuals of 18 thousandths of a foot or 6 millimeters and 15 thousandths of a foot or 5 millimeters were observed. Statistically, the change between distance residual values from no control being applied and 3 control points being applied was on the edge of being insignificant. There was a noticeable increase in vertical accuracy that was probably over and above what could be explained by random error. Now that control was applied for this dataset, I was also able to use the coordinate comparison method. This produced residuals in the northern, easting, and elevation of 10 thousandths of a foot, 12 thousandths, and 11 thousandths, or 3 to 4 millimeters. You may have noticed that the coordinate comparison method provides a smaller number than the inverse distance method. This is because the inverse distance method uses a pair of points and therefore is dealing with the error of both points, whereas the coordinate comparison method is looking at a singular point. These residual values were again very impressive for only 3 control points being applied for a 260,000 square foot project over 3 floors. I then reprocessed the project site with 6 control points, 12 control points, and 20 control points, evenly distributed throughout the project site each time. At 6 control points, no decrease in error was noted from the inverse distance method of comparison versus the uncontrolled data set. At 12 and 20 control points, a minor decrease in vertical error was observed when using the inverse distance method of comparison from the previous data. For example, the uncontrolled data set went from an average vertical residual of 24 thousandths of a foot or 7 millimeters to 12 thousandths of a foot or 4 millimeters with 20 control points being applied. Keeping things in perspective here, we're talking about a 3 millimeter reduction in average vertical error, about the diameter of a grain of sand. The horizontal error actually got a little worse when using 3 control points versus none, but that came back down once more control was added back in. I suspect the vertical error was improved when the horizontal error was not, when control was added in, because the vertical error from the uncontrolled dataset relies heavily on the tilt sensor of the RTC 360, which is quoted at 18 seconds when set up within 5 degrees of plumb, which compared to a typical total station having an angular vertical spec of 1 second is quite a big jump. The coordinate comparison method showed a similar trend. As control was added, there was a very slight decrease in error, less than a couple mil or about a 1/16 of an inch. Next, I wanted to degrade the scan geometry to identify at what point control would provide an obvious improvement to accuracy, and if applying control could save a dataset that was captured using poor scan techniques in the field. So I deleted all the cross-tie links on every floor, then deleted all scan positions and links on the northwest and northeast stairwells, and broke links on one of the southern stairwells on the first floor. This effectively made the north side of the second and third floor hinge entirely on one stairwell and the vehicle ramp. I ended up removing over 200 links and 15 scan setups. I was fully expecting a very significant jump in error between the south side of the first floor and the north side of the third floor because the linking between those two areas was so weak. While there was a noticeable decrease in accuracy, it was much less significant than I had initially expected. With the removal of links and severely degrading geometry, we went from a properly linked, uncontrolled dataset having a horizontal and vertical distance residuals of 14 thousandths of a foot and 24 thousandths of a foot to 20,000 and 23 thousandths of a foot. A very minor increase in average error overall, and the check shots on each floor agreed with the other check shots on the same floor very well, but the vertical error inversing between floors doubled compared to the 20 control point dataset, which made perfect sense. I expected the floors that were separated by weak linking to struggle to maintain good results, and the fact that the average vertical residual between the first and third floor on the new broken link dataset was only 34 thousandths of a foot or 10 millimeters is not bad at all. All things considered, the cloud-to-cloud registration still performs spectacularly well considering the lack of geometry between floors. I then wanted to see if adding 3 control points was enough to both georeference the dataset and clean up the vertical error that I was seeing when inversing between floors. I used 1 control point on the third floor of the northeast corner, 1 on the second floor of the northwest corner, and the last one was on the southwest corner of the first floor. The results seen in this dataset were quite surprising. By applying these 3 control points, it brought in a relatively large amount of distortion to the point cloud and provided the worst results of any dataset seen yet. The inverse distance method gave a horizontal residual of 27 thousandths of a foot or 8 millimeters and an average vertical residual of 53 thousandths of a foot or 16 millimeters. There was a very obvious negative impact when adding the bare minimum control to a scan network with poor geometry and unclosed scan legs. I suspect the control points were having a localized effect on the results of the scan registration. If we look at the coordinate comparison, we can see the points that had control applied fit very well to the total station values as we would expect, but as we traveled further and further away from those points, the error increases. I imagine this did not happen to the same extent when there were closed scan legs and more links, because those links were able to keep the scan network glued together better and moved it more as a singular network instead of adjusting the point cloud surrounding the control points more than the rest of the scan network. It appears that in this dataset, the weakened scan network links could not resist the weighting being applied to the control points as much. I then applied 13 control points to the same project site, and it provided results very similar to what we saw from the datasets that had closed scan legs and good geometry. This indicates to me that the extra control points were in fact able to both shift the scan network sufficiently into its proper location and fix the issues caused by the missing links that we saw in the uncontrolled version of this dataset. The next test I wanted to run was on a project site that had dense scan network linking inside and around different buildings, but those individual buildings were separated by an open area with little geometry to aid the cloud-to-cloud registration, and long links connecting these building datasets. This is where the third project site comes in. This was a scan of 3 warehouse and office style buildings that were all separated by long links of around 40 to 60 feet that I imagined, when not using any control, would significantly increase the error when checking between targets from inside one building to targets inside another building. I was expecting poor accuracy because the low density of links with less than optimal overlap that connected one building to another should have struggled to align those buildings together when only cloud-to-cloud registration was used. To my surprise, yet again, this is not what I saw. There was no obvious degradation in accuracy when inversing between different buildings and when inversing between check shots contained entirely within the same building. With no control applied, using the inverse distance method, I saw a total average horizontal residual of 16 thousandths of a foot or 5 millimeters and an average vertical residual of 12 thousandths of a foot or 4 millimeters. 66 control points were then applied, and using the coordinate comparison method, the average residuals of the northings and eastings were 12 thousandths of a foot and 11 thousandths of a foot, or 4 millimeters, and the average vertical residual was 9 thousandths of a foot, or 3 millimeters. This dataset showed that even with poor linking connecting several well-linked scan networks together, there was no significant decrease in error when applying control versus no control. If you're wondering why so many control points were used on this project, this site was actually scanned by someone else that shared their raw data with me. It does, however, highlight the initial issue that caused the creation of this video in the first place. There just isn't enough information out there on how much control should be used for terrestrial scanning yet. Another job comes to mind when I teamed up with another company on a joint venture project. It was a 100,000 square foot industrial food processing facility. I was contracted to tie in their scan control and process a survey control network with a least squares adjustment. They set over 150 black and white targets in an area with more geometry, less than half the size of our second example we looked at, where I got a 1/4 inch accuracy with just 3 control points. That project site looked like a Dalmatian by the time we were done there. There were so many targets set up, and we wasted days setting control at that density. The final project site was a typical house survey of about 3/4 of an acre. Again, I purposely had areas of poor scan geometry and overlap as I scanned my way through the house, down hallways, and around the house, with the aim to show a situation where someone was rushed during the scan process and skipped a few scans that would have helped triangulate the scan networks with additional overlap. If this was a paid job, I would have certainly added in more scans to help strengthen the network. When no control was applied using the inverse distance method, an average horizontal residual of 34 thousandths of a foot or 10 millimeters was found, along with an average vertical residual of 13 thousandths of a foot or 4 millimeters. These values were quite a bit higher than what we've seen so far considering the size of this project, and I believe it had a lot to do with the poor overlap and poor geometry for the scans to use in the cloud-to-cloud registration. The scans around the exterior of the house in particular had only a wall or two to lock onto and a bunch of grass and trees that were moving in the wind. Really not an ideal situation at all. Times like this are when you should add in those extra scans and shorten in the distance between scan setups to increase overlap. The opposite of what was done on this test. I then added in 3 control points and reprocessed the data. This had a marked improvement on horizontal accuracy, improving it by about 1/3. I processed the data one last time with 6 control points, which I felt was right for a project this size with good scan geometry. This cleaned the check shots right up and cut the error in half. The independent check shots had average residuals in the northing and easting of 5 thousandths and 6 thousandths of a foot or 2 millimeters and 4 thousandths of a foot vertically or just over 1 millimeter. Even with poor overlap, the high-quality least squares adjusted control network was able to get that average check shot residual down to under 1/8 of an inch. Going into this terrestrial scanning study, I expected to see that the density of survey control applied would have a very strong correlation with accuracy. However, this is not what the data showed in all situations. Based on what was seen here, one could make the claim that if a scan network has good overlap and close scan legs, control has very little impact on the relative accuracy of the point cloud derived from that scan network. However, if there are open legs and poor scan overlap, control can have a measurable positive impact on the accuracy of the dataset with what most would probably consider a surprisingly low density of scan control. The data just did not support the density of survey control that I've seen commonly used in the industry. I hope no one watched this video and misunderstood what I'm saying to mean that one does not need to set survey control or check shots for terrestrial scanning. If we want to georeference a project accurately, we obviously must place survey control and align the scan network into that survey control network. But beyond that, independent check shots should almost always be mandatory in my opinion if any kind of accuracy is being quoted. Without independent check shots, there really is no good way to properly qualify a dataset. Using calculated residuals of applied control directly from the processing software often does not give an accurate representation of the quality of the data. What this study has shown, though, is that it may not be necessary to use 66 control points over a 100,000 square foot project site, as was seen on the third project site. Was accuracy degraded by using that much control? It depends on how you look at it. I don't believe that adding in extra control directly degraded accuracy, but if it took 16 hours to set that much control, where 4 hours would have been enough to set maybe 6 to 10 control points plus check shots, and the extra 12 hours could have been used to add in additional scans, increasing overlap, reducing scan shadows, and creating a better scan network overall, it probably would have not only increased accuracy, but given the client a better product overall. This was a long video, but I feel this topic was very important to discuss. I only scratched the surface here. I encourage all of you that process scan data to do your own testing and make your own analysis. In the near future, I plan to replicate this testing scheme using SLAM scanning and to see how a typical SLAM algorithm reacts to control density. So stay tuned for that if you found this one interesting. Thank you all for watching, and as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time.